Hello and welcome to Quick Maths with Spencer Clark. Today's video will focus on explaining the concept of Taylor series in a way that someone with high school level calculus knowledge can easily understand. Before I continue this video, I'm going to assume that you are familiar with derivatives of functions such as polynomials, the exponential function, and trigonometric graphs, as well as limits and summation series. By the end of this video, you should be able to derive a Taylor polynomial approximation and a Taylor series for some smooth function.
Mr. Spencer, I have a crazy friend who says approximations are boring. Is he crazy?
No, just ignorant. See, your crazy friend has never heard of Taylor polynomials. Just ask this scientician. He'll tell you a Taylor polynomial is a way to represent any function as a polynomial that can approximate the function to some degree d around some point a on the function. As we take larger and larger values of d, our Taylor polynomial becomes increasingly accurate. The Taylor polynomial for a function about point a to degree d can be given by these equal equations. To form the Taylor polynomial of a function, we will need to first pick a point x equals a on that function to work from. Sometimes this a will be 0, which is a Maclaurin series. However, a can be any point on the function we are trying to approximate. Next, we will derive the function however many times we need to reach the level of accuracy we want. From that list, we will find the values of our derivatives at the point we choose and write that next to our derivative. We will use a equals 0. Let's take f of x equals cosine of x. We know that cos 0 equals 1, so we write that next to f of x equals cos of x. Then we need to find our f dash 0, which we know to be 0, then f double dash 0, which is negative 1, and so on depending on how precise we want our Taylor polynomial to be. We know that somehow we want our function, in this case cos of x, to equal some polynomial function, which we will denote by this. Let our polynomial equal cos of x. We know from our table that cos 0 equals 1. So that means our polynomial must also be equal to 1 when x equals 0. We can then eliminate all of the other c's since they are multiplied by 0 and we are left with c of 0 is equal to 1, which gives us our polynomial. We can now continue this by deriving both cos of x and our polynomial, and these must also be equal. The brilliant thing about this is it eliminates our c of 0 and then the x on c of 1. We then continue the same steps until we are left with another polynomial with our now known c1. Let's do this again for our second derivative. It's the same method. But now we have found c2. We place that into our polynomial and continue. We can keep doing this until we know cd, where d is the degree of our polynomial. However, notice a pattern forming, here and here. Notice that the coefficient of our constants approach the factorial of the subscript on the constant. From this, we realize that the coefficient of the nth term is given by the nth derivative over n factorial. Now we can go back to the formula you saw at the start of the video, where d is the degree of our polynomial that we had centered our polynomial about some point a, our series would look like that. Try to find the Taylor polynomial for cos x around point a equals pi as practice. We used cos x for our function, but the reality is you can use it for any smooth function. I said before that the larger value for d we take, the better our approximation is around our choice a. Well, when we continue our process to infinity, our polynomial is exactly equal to the function we are approximating. At this point, we refer to our Taylor polynomial as a Taylor series. Here are some examples of functions and their corresponding Taylor series. Well, that's it for the video. We learned how to construct a table of derivatives of a cosine graph and use that table to find a Taylor polynomial that can approximate the function around the point where x equals 0. We extended this to find the general occasion for a Taylor polynomial of degree d, and we learned the formal definition of a Taylor series. I will leave you guys with a short animation of the construction of the Taylor polynomial for cos x around x equals 0 with increasing d. Watch the top of the screen to see the equation. Thanks, guys.